We are about to begin with session number 4, and the topic for this session will be fueling needs of energy sector, fossil, oil and gas, renewables, solar, wind and hydro.
Presentation on the energy scenario, and I have tried to see that what are the areas where the steel, since this particular entire exhibition is about the stainless steel. So I've tried to find out that what are the places where the steel could be used extensively, or there is a need to develop special quality of steel so that you can meet the future energy requirements. Let us start with the present scenario. Presently, we have the total installed capacity of 415 gigawatt. However, this was not able to meet our entire demand of energy. On the 1st of September, we reached nearly 250 gigawatt of peak requirement, and still there was a shortfall of 8.5 gigawatt. That's 8,005 megawatt. We could not meet the supply in spite of having 415 gigawatt capacity. And it is mainly because the large portion of this also consists of the renewable energy, which is not available all the time. This is the breakup of 415 gigawatt, where you can see that the coal plus lignite and the gas together makes more than 55% of the total capacity, whereas the non-fossil fuel sources like hydro, solar, wind are around 100 and odd megawatt. In terms of the percentage contribution to the energy basket, while the installed capacity is 55% on the thermal side, the actual energy supplied is 71%, whereas the other sources are quite less. And that is where the problem is, that we are not able to meet our peak requirement of the energy. So this is the present scenario, that what is installed capacity and what is the share of different energy sources to our energy basket. How does the future look like? In order to look like the future, we need to see that what is our commitment to the environment, because we all know that today world we are facing severe environmental crisis. Lot of extreme weather phenomena are being observed. So India follows the common but differentiated responsibility, which is called CBDR, which was formulated in the UNFCCC conference in 1992 at Rio de Janeiro, where it says that while all the states are responsible for addressing global environment destruction, yet they are not equally responsible. That means those who have caused more carbon dioxide emission, they are more responsible compared to the countries like India, where we have done very less pollution. So while we understand our responsibility towards environment, it is not equal responsibility. As per RBI study, India's GDP growth should be 7.6% per year consistently for next 25 years. As a result, India's energy consumption is expected to grow about 1.5 times faster than the global average over the next 3 decades. That means our energy requirement to meet the quality of life experience of our own population will be much higher compared to the global requirement. So it will be 1.5 times the global average. That means we need to still produce a lot of energy in order to give a good life to our citizen. Now, what did we promise to the Environmental Forum? First time we promised in COP25, and it should be COP21, not 25, I'm sorry for that mistake, at Paris, where I was also present. We committed as a nationally determined target, 40% of our installed generation capacity will come from non-fossil fuel sources. And what is the present? As of 31st March, we have already achieved 40.7% of our total installed capacity of 416 gigawatt, which is from non-fossil sources. So another commitment made was that we will reduce the emission intensity of our GDP growth. That means for per percentage of GDP growth, I will emit less carbon dioxide with respect to what we have done in 2005. By 2030, will be 32 to 35% less. Now, we have already achieved, this was the figure of 2016, this is what I could get, that we had already achieved 2016, by 2016, 24% reduction in intensity. That means we were well on our path of reducing that intensity of emission per our GDP growth. That means we are trying to improve the life of our people without causing much harm to the environment. That is our commitment. Then we further at Glasgow, the NDC target was further enhanced, updated. And now we are saying that instead of 30 to 35%, we will have 45% of emission intensity reduction by 2030. And 50%, earlier we had committed 40% of our installed capacity, which we have already achieved. So we have increased our target and we say 50% of our installed capacity will come from the non-fossil fuel sources. We had also committed for the first time that we will net zero based economy by 2070. And we will have 500 gigawatt of renewable energy produced by 2030. Now these are huge targets. For anybody looking at these figures, it looks initially impossible. But the kind of commitment which the present government has been giving and the way it has been achieving, nothing seems to be impossible. Now, what is the roadmap? If we have to go for the net zero by 2070, then what will be the roadmap? A model study was conducted by World Energy Council India, where I was also as a moderator supervisor. A trajectory has been made on the basis of a model. A mathematical model has been created that how it will vary under different decade. Now, if you look at the table shows what is the figure in 2020, then 2030, 2040, and 2050. And you look at the share of different sources in installed capacity, you will find that the gas is constant. That means we do not expect any addition in the gas capacity. However, we are also not expecting any reduction because this is something which is required in order to generate peak power whenever the renewable energy is not there. But if you look at the coal, it is gradually reducing from 205 initially it is increasing from 205 to 272 gigawatt and then 278 and then reducing after 2040 to 177 gigawatt and by 2060 it will be almost 0 gigawatt. So there is a huge reduction, but for the next 2 decades, there is increase in capacity. And why that increase in capacity? Because we are increasing our manufacturing base, and for that we need faster addition of installed capacity, which the solar and renewable, in the absence of battery storage or in the absence of pump storage, cannot be met. And therefore, this is a necessity for us. So for the next 2 decades, we will go to around 280 gigawatt, and then we will reduce to 177 and then to 0. If you look at nuclear, there is a gradual increase from 6.77 right up to 80 gigawatt by 2060. So there is a lot of thrust on the nuclear. Hydro also is increasing. If you look at the solar PV, from 32 gigawatt to 276, and then 808, and then 1787, and then 3343. That means every decade, we are going to increase our solar capacity 2 times, double. So it is a geometrical progression of solar capacity. And similarly for the onshore wind. And offshore wind, we are 0 presently, but there is a Government of India policy which will further increase this to up to 60 gigawatt. So this is on the installed capacity scenario. This is similar depiction on the graphical. You look at the coal bar, which is gradually going down after 2 bars, and look at the PV bar and the wind bar. So it is how over the decade it is increasing. Now, that was the installed capacity. But what about the share in the energy basket? The total energy basket, today the coal is sharing 71.87%. But in spite of increase in coal capacity in the next 2 decades, we find that the percentage share in the energy basket is reducing to 53.64, then 32.99, then 12.38, and then finally to 0%. And if you look at the solar share, it is increasing to 3.6 to 18.98 to 35% to 50% to 58%, and wind 31.66, and offshore wind also 1.8. Nuclear share is by and large constant. That means while the nuclear capacity is being increased, it is increasing in the same proportion as our demand is increasing. Therefore, the percentage share is remaining same. The same thing is depicted here in the graphical form, that how the coal is coming down and how the solar PV is going up, the onshore wind is going up, the nuclear bar is almost flat, and the gas bar is also coming down. Now this is the scenario from 2020 to 2060. The black line at the bottom shows that how the the coal capacity is going down, and the yellow line is how the solar capacity is going up, and the green line is how the onshore wind is going up, and the line above that is how the offshore wind will go up. The nuclear is a very thin line above the coal, thin yellow line, and the blue line is the hydro. Now, if you look at the typical energy supply demand combination, in a January 2030, a typical day, the yellow line indicates the total demand, and the lines at the bottom, the green and the nuclear and then the orange, these are the blue one. So these are the renewable energy supply, and the blue line below the yellow line is the residual energy. That means after the supply of the renewable energy for meeting the total demand, what is the residual energy which is required to be supplied by the non-renewable, non-fossil fuel supply, and those are the yellow lines. So as you see, the blue line is increasing, the blue area is increasing renewable energy, the thermal capacity generation has to go down, and then in the evening time around 1800 hours or 1900 hours, it starts gradually going up because the solar renewable is not available, so thermal capacity has to be increased. So a typical day, and you will see that what is the position in 2040. Now you see the residual capacity is going into negative side. That means between 11 a.m. to 4 p.m. we have surplus renewable energy available, and therefore there will be negative supply of the coal-based power station. That means, and this negative supply either can be used for producing hydrogen, or we can shut down the plant. These are the two options, and there we find that our hydrogen production will increase because we will have a surplus capacity available. So we'll try to meet the energy requirement from the renewable sources. At the same time, the surplus energy can be used for generating hydrogen. And in 2050, that period has further been advanced, or by 10:30 a.m. to evening 5 p.m., we have surplus energy available, where the blue line is going below the zero. Now let us look at what are the advancements which are being done to improve the efficiency. Advanced ultra supercritical is a technology which has been taken as an R&D project by NTPC, BHEL and IG-CAR, that is Indira Gandhi Center for Atomic Research, to increase the thermal power plant efficiency from 41 to 42% to 46%, which is in percentage term, it is 10% increase, but in actual percent basis, it is 42 to 46. The boiler design is made to work at 300 pressure and 710 and 720 degrees centigrade. Now this requires super alloy in Cornell 740 material to withstand that kind of a high temperature. This composition is nickel 48%, chromium 20%, cobalt 20%, niobium and titanium in a small percentage. Now this material was also developed indigenously by IG-CAR and was tested at NTPC Dadri for high temperature performance, and the performance has been successful. But this is very, very costly material, and therefore The high cost of nickel-based alloy is a major hindrance in going ahead with the demonstration project. We need to develop indigenous capability to manufacture special steels for high temperature performance, as coal is going to be the mainstay of our capacity addition for the next 2 decades at least. So that is what we have seen in the first slide, that how the coal will increase for the next 2 decades. So we need to develop these special steels. We have also successfully demonstrated the welding of alloy 617 and 625 for the turbine rotor, because turbine, the first portion of the rotor will have a very high temperature steam coming at 710 degrees centigrade, and subsequent one are the low temperature. So in order to reduce the cost, we don't want the entire rotor to be made of the high grade steel. So what we have done is, initial first stage we have given the high grade steel, and this other one is subsequently lower grade, and then we have tried to develop that welding technology, which was also successfully demonstrated. Then coming to nuclear, the present capacity is 7,480 megawatt with 23 reactors operating. Out of 6 numbers of 700 megawatt reactor under construction, first 700 megawatt reactor of indigenous design has started operation at full capacity in August at Gujarat, Kakrapara. Now, Government of India, for the first time, Nuclear Corporation has developed 700 megawatt indigenous technology. Earlier, our technology was only for 250 megawatt. Now, a fleet of 10 numbers of heavy water technology has been ordered by the Nuclear Power Corporation, and we will be adding 7,000 megawatt on that. Another thing is a small modular reactor that is going to the future of nuclear. These reactors will be very small, varying from 10 megawatt to 200 megawatt, 300 megawatt, and they can be factory produced. So the scale of production will also reduce the cost, as well as it will also have a higher safety margin. It will have a very small footprint. It can be installed at any smaller area. You don't require huge land. And then you can keep on adding on the modular basis. But this is still in the R&D stage. There are 1 or 2 plants only of a smaller capacity working in Europe and one in China. Government of India has shown interest in collaborating with other countries to develop this technology within the country, and then we can have many numbers of small modular reactors, nuclear plant, which will have a great impact on our net zero capacity addition of 2070. Then new area is offshore wind. Presently, we have 0 megawatt of offshore wind. The MNRE has done this survey of 8 zones identified off the coast of Tamil Nadu and the coast of Gujarat to install these offshore 37,000 megawatt of offshore wind turbines in the next 7 years by 2030. The Model A is for 0.5 gigawatt at Gujarat and 0.5 gigawatt in Tamil Nadu, with a PPA with Solar Energy Corporation of India and the 4-year construction period. Model B is 14 gigawatt with 2-year survey of B seabed and 3-year schedule, and Model C is 22 gigawatt with 3-year survey and 4 years. Offshore wind power will require use of anti-corrosive steel to counter the corrosive climate of sea at a competitive price. So this is one new area where the steel manufacturers will have to develop and see that how the offshore wind can, there is BS standards are notified, and the manufacturers are advised to use only this stainless steel, and you have to have a price competitive. Then comes the hydrogen, the ultimate fuel. It is non-polluting. When it is burned, it only emits H2O, that is water vapor. Can be used as energy carrier for long-haul mobility, marine and shipping, storage, and blending with natural gas. Also as a feedstock for iron and steel, refineries, fertilizer, and bulk chemical industries. Hydrogen is named grey, blue, or green depending upon the source of energy used to produce it. If you are producing hydrogen with the coal, then it is a grey hydrogen. If you are producing with the gas, then it is a blue hydrogen. And if you are using solar energy or wind energy to produce the hydrogen, then it is a green hydrogen. So what is important is that in order to reduce the environmental impact, the green hydrogen should be produced as much as possible. The hydrogen mission of Government of India was announced last year, and the target is 5 million metric tons of per annum production of green hydrogen. 125 gigawatt. That means 1,25,000 megawatt of associated renewable energy capacity, 8 lakh crore of investment, and 60 to 1,000 gigawatt of electrolyzer capacity. Now understand, we are not making large-scale electrolyzer in our country. So this manufacturing base is being required to be set up. And there are a lot of industries which have come forward to do that. So this is a huge potential. And recently you must have heard that there was an agreement with the Saudi government that we will be exporting energy to Saudi Arabia. We are importing fuel oil and gas from the Saudi, but we will be importing hydrogen, which is the energy, to the Saudi, because we have a huge potential of renewable energy. What NTPC has done on the green hydrogen, we have done a small project, pilot project at Kwas gas plant, where we are blending the green hydrogen with natural gas. जो pipeline natural gas हमारा किचन में यूज होता है, उसमें हम ग्रीन हाइड्रोजन हमने ब्लेंड किया 5% और उसको हम यूज कर रहे हैं कुकिंग के लिए. Target is to gradually reach up to 20% blending and study the impact on the gas pipeline. Because the hydrogen is supposed to damage the gas pipeline. So we are trying to see that how much of hydrogen percentage can be carried in the existing gas pipeline. The green hydrogen is produced by electrolysis process, that is electrolyzer, and using the electricity produced by, we have installed 1 megawatt of floating solar plant. We had a water reservoir, उसके ऊपर हमने floating solar plant लगाया, तो ज़मीन की भी बचत हो गई और उससे जो बिजली प्रोड्यूस हो रहा है उसको हम इलेक्ट्रोलाइजर में डाल के उससे ग्रीन हाइड्रोजन प्रोड्यूस करके उसको डोमेस्टिक गैस के पाइपलाइन सप्लाई में डाल के एंड देन वी आर यूजिंग दैट. दिस इज द पायलट प्रोजेक्ट सक्सेसफुली बीइंग डन. दिस इज द फ्लोटिंग सोलर प्लांट फोटोग्राफ floating on the water body, and this is the small electrolyzer and hydrogen storage which is being mixed with the piped natural gas within the plant township. Then hydrogen for transportation also we are doing a pilot project at Ladakh where the green hydrogen is being produced and it is used for running the buses with the fuel cell. 1.7 megawatt solar PV project is producing electricity to produce 70 kg per day of green hydrogen by electrolysis process. और वो 70 kg का हम जो है उसको हम बस में यूज़ कर रहे हैं. NTPC has planned large scale solar PV at Ladakh and use it for meeting local electricity needs as well as to produce green hydrogen for local buses. The problem is that the Ladakh area is very good potential for solar energy, but we cannot transmit that through transmission line because of the very difficult terrain. So whatever we can use locally, either for electricity or for the local transportation, or maybe we can think of producing hydrogen and then transporting at least into Jammu and Kashmir area so that we can save on the huge cost of transportation and the huge cost of transmission line. Then comes the hydrogen IC trucks. So for mobility, you can use hydrogen in two ways. One is using the fuel cell and another is using the hydrogen in the internal combustion engine. The present ICE burns diesel. Now you can also burn hydrogen in the internal combustion engine so that the emission is zero pollution. And Ashok Leyland with the Reliance have already developed truck of 19 to 35 ton capacity. And the advantage is that you don't have to do much modification on the existing engine. So it is very easy to adopt. If you are talking about fuel cell, then you have to have a new engine which is fuel cell and the rotating parts are removed. Whereas in this case, with minor modification, you can use the hydrogen for the transportation process. The major challenge in hydrogen transportation is the technologies that enable the transport of commercially viable quantities of hydrogen in bulk are still in developmental phase. This is because hydrogen is particularly challenging product to safely transport. It has the lowest density of all gases and is also highly inflammable when mixed with the smallest amount of air. We all know that hydrogen mixed with air can become very explosive. A common misconception is that the transport equipment designed to carry LNG could be easily adopted for hydrogen. But this is definitely not the case. If you compare that, the compression required for LNG is only 3.6 psi. But for hydrogen, it is 11,600 psi. The liquefaction temperature for LNG is minus 160 degrees centigrade. For hydrogen, it is minus 253 degrees centigrade. The flammability in air for LNG is 15%, and for hydrogen it is 74%. So it is very difficult to use existing LNG pipeline to transport the hydrogen. Although transporting gaseous hydrogen via existing pipeline is the low-cost option, the high initial capital cost of new pipeline construction is a major barrier. Research today, therefore, focuses on overcoming technical concerns related to pipeline transmission, including the potential for hydrogen to embrittle the steel and welds which used to fabricate the pipeline. So this is even stainless steel material is very much prone to hydrogen embrittlement. Therefore, we need to have technology so that we can minimize this impact of damage of the steel pipe because of the hydrogen. Then the need for lower cost, more reliable and more durable hydrogen compression technology. As we have seen, the hydrogen required to be compressed to 11,000 psi. So we require more higher compression technology. Potential solutions include using fiber reinforcement polymer pipelines for hydrogen distribution. The installation cost for FRP pipelines are about 20% less than that of a steel pipeline because the FRP can be obtained in sections that are much longer than steel, minimizing the welding requirement. This is a challenge for the steel industry, that how do we substitute ourselves and promote ourselves in order to transport large-scale hydrogen. The solution, another solution for transporting hydrogen is that we can convert into a chemical compound which is already widely used in the world, and that is ammonia. So you can convert the hydrogen to ammonia, ट्रांसशिप अमोनिया को शिप से हम ट्रांसपोर्ट कर सकते हैं, और जहां हमारा यूज़ होना है वहां अमोनिया कैन अगेन बी कन्वर्टेड इनटू हाइड्रोजन एंड इट कैन बी यूज्ड. Compared to hydrogen, liquefied ammonia is far more convenient, practical, and cost-effective to transport in terms of both the required temperature and pressure conditions. Once the ammonia reaches destination, it can be used directly as a fuel for gas turbine, for lower carbon power generation, or can be converted back into hydrogen. Thank you.
First of all, I thank the organizers for inviting me for this session. I come from the other end of the green spectrum. I've come from the oil and gas industry, so very far away from any green initiatives. I understand the theme of this conference is stainless steel creating a green and sustainable future, which is very relevant for today's world. Having said so, talking about hydrocarbon, this has been the backbone of our energy segment for the last over a century, and will continue to be there for a while before it gets completely displaced. According to a EIA study, the world energy requirement is going to go up by around 50% from 2019 to 2050. I did a comparison with the last 30 years, that is 1980 to 2010, and it has gone up by 63%. So technically, by all logistics, 50% is conservative to realistic. So we need to be prepared for that kind of a growth in energy consumption worldwide. We are also seeing a significant change in the energy sources, with renewables likely to grow by around 3.1% for the next 30-40 years, whereas hydrocarbon, especially gas, is at 1.1. Fluids are down to 0.6 and coal down to 0.4%. So there's definitely a significant shift in the fuel for the energy generation in the next 40 to 50 years. But one thing that we need to bear in mind when we see these percentages of 1.1 and 0.6 for hydrocarbon, we need to bear in mind that the hydrocarbon or fossil fuel as such is a finite fuel, and there's an inherent decline in production of all the fields around the world. So 1.1 doesn't really mean that hydrocarbon is going to grow at 1.1, because it has to cover up the depletion or drop in production, which is going to compound to the added growth. Again, one more thing, observation that I can see in the slide is that the share of renewables is going to grow significantly higher because of the higher growth rate compared to the fossil fuel in the next 4 to 5 decades. Coming to the energy basket, I don't want to touch much. We have already heard it from our moderator. So India is leading the pact, going green. Our solar share has significantly grown. Though we had committed by 2030, we have already crossed 40% of renewable energy, bulk of it coming from solar. And we are committed to 30 to 35% in reduction in carbon levels, carbon emissions. Coming to the offshore industry, offshore wind and offshore tidal and offshore wave, as per an MNRE study, it is believed that we have a potential of around 12 gigawatt of power that can be generated from tidal energy and 41 gigawatt of power from offshore waves. There's also a potential of about 140 gigawatts of wind. This is very nascent as of now because the cost of production and cost of capex is very high, but it's just a period of time before the technology matures commercially to become viable. Interestingly, all these models, be it tidal, be it wave, and wind, offshore wind, have been proven technically fine, and in fact, it is far more easier to manage for a couple of reasons. One, it doesn't have any disturbance with our normal day-to-day life. Second, the sources are very, very consistent. For example, the wind offshore doesn't have much of variation as what we can have in land. The directions doesn't change much. Therefore, the utilization factor improves significantly. Coming to tidal, driven by the moon and the sun. So as far as the solar system exists, the tidal energy is going to be there, and it's going to be consistent. Coming to wave, it's a combination of wind and tidal that again becomes consistent in the offshore environment. So in terms of capacity utilization factor, offshore sources can be much, much higher as compared to the onshore. For example, we are talking about solar onshore, the capacity utilization factor of as low as 10 to 20%, whereas tidal is in the range of 65-70%. So that's a kind of paradigm shift in terms of energy source when it comes to offshore. Coming to the environment, as Mr. Jai has already touched upon, when it comes to offshore environment, we have high salt content, corrosive environment, and therefore the selection of material is very, very critical. As I said, I'm not a metallurgist. As the closest I've been to is two of my colleagues, Malcolm Gray and Mark Dale, with me, sharing an office back in Singapore many years back. So my knowledge about metallurgy and material science is pretty low. But having said that, what we have seen is typically stainless steel 316 has got pitting issues in offshore environment. Therefore, 6MO is far more effective in terms of usage in offshore industry. Plus, duplex and super duplex are widely being used in the industry. One more thing that we have seen that the industry has taken benefit of is in offshore oil and gas, we have umbilicals, which are flexible steel cables coming to the platform or to the FPSO. And these have gone through huge development over the last 40, 50 years. And those experiences and issues that we face there are being translated into offshore power generation, where again you got the power cable to be connected to a floating platform or a moving element and need some certain amount of flexibility. And at the same time, you're subjecting it to a marine saline environment. Some of the corrosion issues that we have seen in the marine environment, pitting corrosion, typical because of the saline environment, stress corrosion, and crevice corrosion. So as I said before, we are finding 6MO far more corrosion resistant in marine environment than normal SS316. Plus, we have extensively used duplex and super duplex material in some of the applications. Interestingly, everything comes with a cost, and the cost is an important factor offshore as well. What we need to bear in mind is any intervention in offshore environment is going to be far more costlier than what we would normally have it in onshore. You need a vessel to go and stop or intervene with the equipment. There are weather restrictions because the vessel may not be able to go in and out all the 24/7. So all this adds a lot of cost when it comes to offshore installation and maintenance. Therefore, spending a little more on capex and making the life longer makes it a lot more sensible in the offshore industry. So, to conclude, stainless steel definitely has advantages in the marine environment. It's an excellent choice for marine application due to their exceptionally corrosion-resistant durability. They are easy to maintain and require little upkeep, making the cost-effective solution in marine projects. Future of stainless steel in offshore application is bright indeed, because you're going to have more smaller applications. A platform is huge, it's significantly carbon steel, but when it comes to lighter facilities like the offshore wind or offshore turbine, tidal or wave, the application of stainless steel is going to be much higher. So with that, thank you very much.
So when we come to the energy sector, oil and gas or renewables or fossils, main important thing is the material selection criteria and what the engineers are doing. They are looking into the aspects, what are the chloride levels, oxygen, sulfides, H2SO4, all these elements. They are considered as the process conditions which stay over there, and then the structure application or structure conditions, what you are going to make and what are the standards over there. Then on the material properties, while selecting stainless steel or any other material, what we are considering is corrosion resistance, which Mr. Matthew covered, whether it is a uniform, localized, stress corrosion cracking, or the mechanical properties of any material, or availability or fabricability of the material, or the economic factors, that what is your design life expectancy, what is the reliability, and at the end, what is the life cycle cost of the material. So you will see the two pictures over here in the same environment. On the left hand side, you can see the 316L, which has corroded after a couple of years, and on the right side, the same environment, you see duplex 2205, it is still clean. The issue with 316L is it has a limited resistance to the uniform and pitting corrosion in the harsh environments, and it is susceptible to the stress corrosion cracking, and very moderate mechanical strength in comparison to some other materials. So there are environments where 316L is not sufficient. So solution you have is either you shift to the ultra high alloyed stainless steels or nickel alloys, or you go for the FOTA range or duplex stainless steel, where you use the higher strength or higher corrosion resistance or combination of both. Talking about the general characteristics of ultra grades and FOTA grades, ultra, they are austenitic, they are non-magnetic, can be used in wide range of application, different temperature range, very good resistance to uniform and uniform corrosion, good to exceptionally good resistance to pitting and crevice corrosion. The PRN number, which is the how you mention or mathematically calculate the corrosion resistance, is called the PRN number, which is percentage chromium plus 3.3 times of molybdenum plus 16 times of nitrogen. If you add that, you get the PRN number. Higher the PRN number, better is the corrosion resistance. So in austenitic ultra grades, the PRN goes from 28 to 56. 56 in 654 SMO that was talked in the last presentation, which has a 56 PRN, one of the highest known corrosion resistant stainless steel as on date, with 0.5% nitrogen. And it has a very good resistance to stress corrosion cracking, good formability, and it is non-magnetic, which I said. But then there exists a solution with the FOTA range, where it is a austenite plus ferrite structure in the same material. It can be used in a limited temperature range from -50 to 250 plus degrees centigrade. The PREN is from 26 to 43. Yield strength values is normally more than 400 megapascal. So you can use the strength of this material in comparison to the austenite to design your product. It has a low thermal expansion, very high absorption and good fabricability. So which is most cost-effective solution? Coated carbon steel or duplex stainless steel? That is what the process industry normal says, that we are using a lot of carbon steel. So should we go to the stainless steel? Why we cannot go? It is too much costly. So let's try to cover that. There are two aspects into that. One is the material cost. Then there is an initial cost of the material, which includes the fabrication or welding cost. And you can use the strength of the material, as I said, that to reduce the thickness, make the equipment lighter. And then there is something called the maintenance cost, which is a repetitive maintenance cost like coating, painting, etc. And then you get the total cost of the material in the initial investment. And when you add the repetitive maintenance, you get the life cycle cost over the design life. So I'll just try to cover, as I said, I'll talk about the cost. I'll try to take an example for photo duplex in crude oil storage tanks and pipes. So the applications we can see in the crude oil storage tank, one is the bottom plate or the first core of the tank. Because on the top core you don't have much of the corrosion, and on the annular ring you have to use, or you can use in the foam water pipelines across the tanks where you can avoid the corrosion of the material. So there are two applications. So crude oil storage tank for the oil industry, carbon steel or duplex stainless steel. Let's go like this is a case which we have taken. The diameter of the tank is 79.5 meter. I request everyone who is present just go through the numbers. These are very critical numbers and actual numbers that exist. The diameter of the tank is 79.5 meter, height is 18 meter, relative density of the oil is 0.85, and temperature I have considered 50 degrees centigrade because at the coastal areas in India, the temperature is normally 45 degree plus. So you need to take that into consideration. In Europe, the ambient temperature is 20 to 25 degrees. So those solutions doesn't work over in India. And on the material side, this is what we have taken. The bottom plate, as I said, comparing A36 carbon steel versus Super Duplex 2507. Length of the sheet 12 meter in both the cases. Width of the sheet I have taken 2 meter on the same side, both the grades. Thickness 8 mm in A36, which is a designed actually used, but when you go to the Super Duplex stainless steel, you can use the strength of the material, which is 500 megapascal plus. You can reduce the thickness to 6 mm. In fact, you can go to 5 mm also, but the design standards of code doesn't tell you to go lower than 6 mm. Area, if you work out mathematically for A36, it is 4803 meters square. On the 2507, the same area. The weight of the bottom plate will be 330 metric tons for one tank, whereas in Super Duplex, it is 247 tons. Similarly, on the annular ring, which you have to use, ring width is 0.7 meter in both the cases. Thickness in Super Duplex, we have suggested 14 mm in place of 16 mm, and ring area is 188 meters square, same, and the weight has reduced from 28.1 to 24.6 metric tons. So what we have to remember, in A36 carbon steel, presently what they are using is 338 metric tons of for the bottom plate and 28 metric tons for the annular ring. In Super Duplex, you have the some saving. So when you go to these numbers, like A36, the cost of the material, I have taken 950 euros per ton. Super Duplex, 6,700 euros per ton. That is the cost of the material, CIF India basis. So if you look into the relative cost, taking carbon steel as a reference, the cost of duplex stainless steel Super Duplex is roughly 7.05 times than that of the cost of the A36 carbon steel. And here is the point everyone stops. They say stainless steel is very costly, but that's not the case. Now what you have to do, I have multiplied 950 by 1 and 6700 by 950 by the weight of the material that we calculated in the last slide for bottom plate plus annular ring. So you get a cost for the initial material 340,000 euros. And for the Super Duplex, it is 1819720. Since we have reduced the weight, you can see that relative difference of 7.05 times has reduced to 5.35 times. Still, it is very high. Now, what you have to do, you have to weld the material. That is important. And on the left side table below, you say we have considered the same weight that we considered in the last slide. Weld and assembly cost 20 euro per meter for carbon steel, and in super duplex we have taken higher cost because the cost of the electrodes will be slightly higher, so 30 euro per meter. Length of the weld will remain same. On the annular ring, like weld and assembly cost, we have considered 40 and 60. Length will remain same, and then there is an additional cutting cost for the annular ring. So 550 we have taken the length, and additional cost in super duplex we have taken higher than the carbon steel. And on the surface, okay, so going to this one, if you calculate these values, the total welding and assembly cost for A36 carbon steel works out to 85,000 euros, whereas in super duplex it is 127500. And on the right side table below, you see the surface treatment cost because you have to do the coating of the coating on carbon steel. When you coat the carbon steel, the cost is 9.75 euro per meter square, and the surface area remains 96. On the super duplex, you see I have taken only one side, this 4800 meters. Reason being that you do not have to coat super duplex, but then you have to spend some money on cleaning the weld oxides and cleaning the area, pickling. The cost is 1.5. So if you calculate that surface treatment cost, the total cost, if you see the relative difference between carbon steel and super duplex has reduced to 3.77 times in comparison to what we started with 7.05, and these are the practical numbers. Now, what does the standard say? This is a screenshot from API 653, which is being used, and it says, you see the section 4. They say if you are using these grade duplex or super duplex, you can increase the inspection life by another 10 years. Normally, what oil and gas industries are doing, they are designing their tanks for 30 years, and every 10 years they do the inspection of the material and have to change these bottom plates because they corrode. Not because of crude is not corrosive, but what happens, sir, like when the vessel comes over in India and they empty the vessel, then they flush it with the seawater. And if you see, the standard says or normal study says that you have to have a settling time of 72 hours minimum before you can, the sludge will settle and you can take it out. But we do not have that much of capacity in India. The maximum declared holding time is 32 hours, I think. Before that, you have to flush it to the next stage. So we have this challenge and we have to gather this. So roughly, this is the what standard says. So you can increase the inspection life by 10 years. Okay, so coming back to the calculation, we started with here, like you go to the relative cost, 3.77 times, it is costly. And every 10 years, you are maintaining the cost, you are replacing the bottom plates in carbon steel. For a stainless steel crude oil storage tank, the declared time is 9 months. The tank is being shut down, and out of 9 months, 90 days is the time that is taken just to replace the bottom plates. You can verify or vet these numbers with any oil and gas companies, and they will give you the same numbers. So what if this bottom plate remain as it is and not has to be replaced? You are saving the 90 days, and maintenance cost is 6,650 euros per day. This is worked on the basis of like each contract value. If you see from the oil and gas companies, because these are on the public domain, it is 598,500. That is the typical contract value, and if you calculate with this, it is boils down to 6,650. Replacement cost 340,195 just for the material, but actually you have to coat carbon steel and do 518,795. And then service life of 30 years, it means you need to have 2 replacements, one after 10 years and after 20 years. Then there is some depreciation cost because in duplex stainless steel or any stainless steel, at the end of the service life, you can get some scrap value, but in carbon steel, hardly get any scrap value. To have to consider that cost also. So lost production value in A36 is shut down of 90 days, and lost production value is 2,500 euro per ton and 2 number of shutdowns. So if you calculate that cost, the total life cycle cost of carbon steel works to 3257,366, whereas in super duplex it is 1954420. It's a pure mathematics. You'll find that within 30 years, super duplex stainless steel, which was 7 times material costly, it works out to be almost 50% cheaper than the carbon steel. This study, like I've taken 40% because of initial investment. You might have to spend some money on the financing or etc. So roughly 40%, and then at the end of the service life, you can carry on the same tank for another 10 years. And if you calculate these factors, put in these numbers, you'll find the cost will reduce to 65%. No rocket science, pure mathematics on that. Okay, coming to the tubes and pipe, mild steel or duplex pipes. 14-inch tube, OD 355.6, 50 bar pressure, temperature 50 degree, weld factor 1, calculated according to EN 13480. And here what we have taken is mild steel, 250 megapascal strength, another is 355 megapascal strength, and we have taken lean duplex LDX 2101 with the yield strength of 480 megapascal. And when you use the carbon steel, normally they are adding 3 mm of corrosion margin in the 3 mm into that. So worked out design thickness according to this standard for that pipe is, for these conditions, is 5.4 mm, 3.8 mm and 3.3 mm. In carbon steel or alloy steel, you have to use 3 mm. So the final thickness, usable thickness is 8.4, 6.8, whereas in super duplex or any duplex grade, you don't have to add the corrosion margin. Because if you see the values of corrosion on the ISO charts or any corrosion figures, it is less than 0.1 mm per year. So you don't have to, so you can use the thinner gauge in LDX 210 or any other grade in comparison to 250 or 355. For this size of the pipe, kg per meter, if you see, weight is 73, 59 and 29. Material cost 1.08, 1.17 and 3.83 euro per kg. Tube material cost is 79 for 250 megapascal strength, and with mild steel with 355 mm high strength is 69, and for duplex it is 111 euro per meter, which means duplex in the initial is still costlier than the carbon steel, whether it is low strength or high strength. Now what you have to do, you have to coat these tubes when you are using the carbon steel, and in duplex you don't have to do the coating, you have to simply clean the weld edge and do some pickling, so minor cost has to be taken. And we have considered 2 type of coating. One is the low cost coating, cost is 27 euro per meter, and coating with epoxy that we have considered 50, that is slightly higher. And on the duplex we have taken only 10 just to clean the pickle welds and some edges. Surface area will remain same, 1.12 meter square. On the right side table, if you see, when you put these figures, in mild steel, material when you are using with low cost coating, whether on one side, on the both side, on the bracket it's on the both side, when you are coating on the both side, depending upon the application. Mild steel it is 106, 133, whereas in epoxy coating 129 and 179. Similarly, when you go to the duplex stainless steel, it is 121, and whether you do one side or both sides. So in comparison, duplex in the initial stage itself is working out to be cheaper than the carbon steel. I'm not talking about the service life or maintenance or something. So wall thickness plus coating, again not talking about the maintenance cost. When you use the lower thickness, you have the flow area is more flow area available when you are using duplex, so you can push more material into that, more liquids, and increase your capacity. So duplex stainless steel pipes ends up with a price that compete with the coated carbon steel. You have seen the pictures. This if correct duplex grade is to be used, there is no need for maintenance of pipe. This is also important. It is not just like that you use any duplex steel for any application. You have to select the right grade depending upon the media and what are the applications over there. LCC we have seen. Sir, you touched upon this high temperature grades. You mentioned about the supercritical boilers or high temperature grades. So this is something new addition, 800, 800H and 800HT. And these grades are capable of handling the temperature more than 800 degrees centigrade. I'll not get much into these details, how it is done, but this figure is very important. The dark line that you see red, it is a 253 Ma material, which is 253 with micro alloyed grade, which is presently being used up to 1050 degrees centigrade in the furnace or something. On the bottom side, dotted line, you see 310S, and the creep strength of the 310S is much less than 253 Ma when you are using at the higher temperature. Presently, in almost many industries or power sector or even in the cement or other industry, 310 is being used, but people forget that it doesn't have a good creep strength. 253 Ma has a very good creep strength, but if you still need a very high creep strength, you have to switch to this ultra thermal alloys 800H or 800H HT, which is more important. These are some application areas where you need the high creep strength of furnaces or petrochemical industry, whether cracker tubes, reformers, piping system, caustic soda production. Yes, coming to nickel alloys, Mr. Jha touched upon the cost of the nickel alloys, and yes, that is true because nickel is very highly volatile on the London Metal Exchange, and every industry is dependent upon that. So, but let's see, stainless steel, if there is some solution. One thing, let me clarify that as I mentioned earlier, that you need to choose the right duplex grade. Similarly, you have to choose the right stainless steel or nickel alloy grade, because with the change in the environment, the properties of each grade or each material change. If you are talking about the chloride conditions, this is the relative corrosion resistance. You start with 316L, then 904L, 825, 254 SMO, and then go to 625 or 276 or ultra alloys. But if you are talking about 70% sulfuric acid, you see the picture change. After 316L, the 254 SMO has shifted on the left, whereas 256, 54 SMO and C276 has gone up. So this is something you need to discuss with the material engineers, that which grade and which application you need to select. This is one of the new addition in Cenicro 35, which is Autocompo has added. In fact, this is a grade by Alima, earlier Sandvik. So what was happening, like people were using Super Duplex 2507. And if Super Duplex was not sufficient, they were switching directly to 625 because there was nothing available in between for those applications. So there was no solution. So this grade has tried to cover that part or bridge that gap. It's a newly developed grade. It's a combination with a very high performance. It is austenitic, stainless steel and nickel alloy. Grade is excellent corrosion resistance in combination with the higher mechanical strength. Very good resistance to pitting and corrosion and even to the stress corrosion cracking. Very suitable for seawater applications. High resistance to uniform corrosion in acid and caustic environments. High resistance to erosion corrosion. Very high mechanical strength. Good fabrication properties such as forming or welding. This is the composition, chemical composition. Like let's try to compare it with alloy 625 on the bottom. Alloy 625 has more than 58% nickel, and what we have done over here is nickel has been reduced to 35, which means you have a lot of saving on the material cost, and final product works out to be cheaper one. We have reduced the molybdenum, so not much dependent upon the ferromoly cost, and both are austenitic. Some copper has been added, and chromium has been increased from 20 to 23% to 27% over there. Now coming to the properties, let's compare only Cenicro 35 and 625. First thing is the RP yield strength of the material. In alloy 625, you're talking about 379 in the hot rolled condition, whereas in Cenicro 35 it is 350, almost comparable, and the cold rolled form also it is more or less comparable. Mechanical strength also you see it is more or less comparable, but when you talk about the elongation of the material in Cenicro 35, in 625 it is 30%, whereas in Cenicro 35 it is 40%, which means you are able to fabricate or form the Cenicro 35 much easily. And these are the standards mentioned. Looking into the physical properties, the density of Cenicro 35 is less than alloy 625, and modulus of elasticity more or less comparable. More or less everything is comparable. So what you have is, and these are some of the applications that we see is the heat exchanger, tube plate, seawater, brine, chlorinated inorganic acids, or scrubbers, or flue gas cleaning, where we see a lot of application, and this grade can replace 625 and C276, where the availability of the material is poor and cost is very high. So it has a good or better resistance to alloy 625 in chloride containing environments, is optimized, good fabricability, offers cost efficient alternative to nickel alloys. And when I say cost efficient, normally everyone will be interested to know the price differential. So you can see with the same properties, you can get roughly 20% less cost in Cenicro 35 as compared to 625. So you have a direct saving. And our estimate is roughly, I think, 30 to 35% world market share. People are using 625 because this grade was not available. So this can bridge the gap. Thank you.
As Mr. Jha very correctly says, the acceptability from the project authorities on life cycle cost analysis is very, very minimum. Although we have also been trying for mild steel compared to pre-stressed concrete. What is there, one major success we have achieved that in the general finance rule, they have now included that life cycle analysis may be made. This may word we wanted to be changed to shall, but this has not been agreed to by the finance ministry, and that is the current scenario. Now the point is that, all the project authorities, they are going by the, as Mr. Jha very correctly says, initial cost of the material. And there you have shown between A36 and 2507, there is almost 4 times the initial cost. One very good analysis this you have done. Now, one point that you could have done to convince the project authorities is that what is the particular break-even point where, these two costs will be comparable as maintenance is nil. So what is that point? In fact, your convincing argument should start from that point of view, which is be somewhat, it may not be for 30 years, it may be in between, say, about 18, 20 years.
But there is payback period.
So,
payback period.
Yeah. So that is the point where you can, try to convince them. That is number one. Number two, to you, sir, one point I want to mention. You have shown in your presentation the non-renewable energy, that is gigawatt. 500 is now the current target up to be achieved up to 2030. Now, the current scenario, currently, I think you have shown, if I remember, it is about some 216 or 220 megawatt, is it? So there is a big gap of 220 megawatt. Are you, what is your kind of, the confidence that we will be able to achieve that, by, say, in another 7 years' time, the kind of, the consumption pattern that is going on? My second point is that you have shown coal use to be fossil fuel to be used for production purposes almost nil by 2040 or 50?
60.
2060. Whereas I think Mr. Matthew's presentation shows it will take a longer period. Now, and if I remember correctly, the Ministry of Mines, very recently they have come out a long-term vision plan of coal industry where they are saying that even by 2060, coal use will be there by the industry, particularly steel is one of the major factors. So I think if you see the alternate scenario, everything comes to the cost of material or cost of procurement. So whether the energy cost will come down so heavily so that, it will naturally influence the consumers to consume much less amount of fossil fuel and more amount of, renewable energy. I seek your views on.
In fact, one thing, what Mr. Matthew had shown is the global trend. And what I had shown is what India. Second thing is that what I have projected is that if the government of India commitment of net zero by 2070 is to be achieved, then what will be the transition roadmap So this is something which we need to follow in order to reach that goal which we have set for ourselves. So whether it will actually happen or not will depend on how do we, unless we have a roadmap, we cannot even think of doing that. You see, earlier, if you remember, before 2014, the target was of adding 22 gigawatt of renewable energy, which was suddenly improved to 175 gigawatt by the new government. And of course, we did not reach 175 gigawatts. And probably for that, the COVID period was a major bottleneck of the 2 years. But we have done very good compared to our initial 22 gigawatt. So that is one thing. We are almost now nearly 100 gigawatt, which we have done. And the biggest shortfall has been on the rooftop solar. And also for that, there is a reason. The reason is that the rooftop solar, there is a concept of net metering versus gross metering. Because you have to sell that power, surplus power, to the electricity board. And electricity board is not interested in net metering. They are interested in gross metering. So it is becoming a deterrent for the people to put a rooftop. Because you have to buy power at 8 rupees and you sell only at 2 rupees 50 paise. That is something which people are not very happy about. So the moment you change this, then a lot of rooftop solar will come. And that will be like, I remember one of the quote of a British power industry head, when he said that we will have the people as a generating company. So everybody's house is a generating company, and only for a peak power requirement, they will like to be connected to the grid. So that is what is the scenario should be in future if we want to save the environment, save this earth. Your second question was with regard to the coal projections versus the renewable projection. Now you already know that the renewable power, at one time it was 12 rupees, it came down gradually to 4 rupees, and it was as low as below 2 rupees for some time, and now it is stabilized at 2 rupees 40 paise around. So it is definitely much cheaper today itself than the coal power. However, there is the battery storage cost is not there, the transmission line cost is not there. So if you add all these costs, it will come slightly higher than the coal cost. But if you look at the increase in the trend of the coal price over the period of time, and it is a monopoly, we all know that. So the coal prices keep on increasing, whereas the price of the renewable energy is fixed for next 25 years because there is no fuel. So it is only the capital cost. The fuel cost is zero. So there is no likely increase in the price. So if 2 rupees 40 paise I am selling energy today, and look at the devaluation of rupee, what will be the 2 rupees 40 paise in 25 years from down the line? So naturally the coal will become a loser. But the question is that there is no question of winner or loser. The question is that we have a commitment to the environment, to the mankind, and we need to have a transition which improves the life of our people, which meets our energy demand. At the same time, we meet our responsibility to the environment.
One thing I would like to share that this calculation has been totally accepted by the technical team of Indian Oil Corporation pipeline division. Only because of some procedural or something, as you say, May word is there for which everyone is trying. It could not be made applicable from their finance team, but as far as technical team, they are fully convinced. And recently, I think in some of the application, at least not in the crude oil, but for other applications, duplex stainless steels have been used in India. For the storage tank, probably, I think if I remember, Technip itself completed a project at IFCO Paradip, wherein they supplied 857 tons of the duplex stainless steel tanks almost 1 year back. So we are looking into more and more demand in coming to that.
And people are very cautious in allowing something which on the face of it looks like that we are buying costlier thing than what is available in the market. But what about the private players? Such questions are not being asked in the private industry. So whether it is very easy to convince the good private players first, like whether the Reliance is going for that, because they are doing a large scale in oil and refinery sector, and if they are doing it, they see value in that, then it is easier to show that as an example and then convince the public sector than the other way around. Because for private sector, it is easy to take that decision.
Actually, I think it's not about the public sector or private sector. It is about the acceptability from each individual of us. Like you're also traveling in Delhi. If we take any Ola or Uber, it takes us, like for me, I stay in Faridabad. It takes me around 35 minutes in the morning to reach airport. If I go for the blue smart cabs, it is taking me 1 hour. Slightly higher cost, but I'm preferring that. Reason being that at the end of my trip, I get a notification that I have been able to save this much of CO2 by this ride. Going to the FMCG industry, we are going to the market in the shopping malls, and now I've seen shopping malls pitching like, okay, if you are buying this material, this stuff, this is made out of the recycled material, this is the CO2 emission. So we are ready to pay for that. So I would say those acceptability and perception has to come from each individual of the person from the country, and they have to start demanding. Now, talking about the private sector, my experience has been that acceptability has been good at both the ends. I was struggling with the project even in the PSUs where we had some issues with the standards which were being used. And they were able to guide us that, okay, if this standard is not working out, probably this is the other way to handle this standard. But I think acceptability is same at both the ends. People are good. You just need to find the right people who are ready to understand and actually who are actually engineers and I won't say engineer by education, but who are ready to take the next steps to do some disruption in the industry. Because if you have to grow, that is, I think, has been talked about in G20 also. If you have to grow, you have to do some disruption.
You have shown the life cycle costing over a period of 30 years. I think if you show the costing over a period of 60 years, the cost of scrap would probably be the same as the cost of raw material used in the beginning.
Correct, sir.
So your cost is net zero.
Yeah, correct.
Thank you.